So in this video, I'll explain how to complete problem 13 from the chapter 3 homework. So that problem states to calculate the wavelength in nanometers of the spectral line produced when an electron in a hydrogen atom undergoes the transition from the energy level n equals 7 to the level n equals 2. So I read through that problem because I wanted to make sure that I highlight certain things. And so anytime you're dealing with the word problem, read through it one complete time, then go back and dissect it, figure out what information is given, because that often gives you clues as to what equation you need to do or how to complete that problem. So with this one, there are a couple of clues in that problem. One, it tells you to calculate the wavelength. It talks about a spectral line. It talks about the electron in a hydrogen atom. It also talks about a transition and that we're going from n equals 7 to n equals 2. All of those are clues as to what's taking place because we're dealing with trying to identify the wavelength of an electron in a hydrogen atom that's involved in a transition. That's a clue that we're going to be dealing with the Rydberg equation. So his equation is 1 over the wavelength is equal to the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. These are just the energy levels, the first level that you're starting with, so we can also show it as n initial. The final level that we're ending up with, or the second level that we're going to, we can call that final. So they still mean the same thing. So we can do either one of those. It's still just telling us where we're starting, where we're ending up at. And then the Rydberg constant is 1.096776. We can often just show it as 1.097 times 10 to the 7th, and that's inverse meters, so 1 over the meter. So keeping that in mind, we have the Rydberg constant, we have the first energy level, we have the second energy level, so we can simply plug into this equation to calculate the wavelength. And so again, 1 over the wavelength, so this is what we're trying to find out. The constant, 1.097 times 10 to the 7th, inverse meters, times the difference of 1 over, we're starting at the 7th level, we're going to the 2nd level. So if you need to see this one calculated, remember we have to square those values. So that means that we're looking at 1 over 7 squared is 7 times 7, which is 49, minus 1 over 2 squared, so 2 times 2 is 4. And so once you have this set up, you can then do that calculation. And once you put that in your calculator, you'll get, I'm going to put the extra significant figures initially. It's a negative value, 2518622.45, and that's inverse meters. Now, I'm going to go ahead and rewrite 1 over the wavelength, because if you keep track of this, you'll see that we haven't actually calculated the wavelength. This is the inverse wavelength. So in other words, this is 1 over the wavelength. And so if this is 1 over the wavelength, I'll just rewrite it. If this is 1 over the wavelength, then we have to think about how would we actually calculate the wavelength, because that's what the problem is asking us for. And so in order to calculate the wavelength, if this is 1 over, we have to flip it. So we have to imagine 1 over all of this, 1 over all of this. When we do 1 over the wavelength, that's going to leave us simply with the wavelength. When we do 1 over that negative 2,518,622.45 inverse meters. Once we put that in our calculator, it's going to give us a negative 3.97 times 10 to the minus 7 meters. Now, if the problem we're asking for meters, we will be finished. But we always have to look at what is the problem asking us for And does it specify the units? And it does. It asked us for the wavelength, and it asked us for the wavelength in nanometers. So it stated it in the problem, and it showed it on the answer blank. Right now, we have our wavelength in meters. So we have to actually complete another conversion to convert it to nanometers. So if our wavelength is shown to be a negative 3.97 times 10 to the minus 7 meters, we have to convert it. In order to convert it, we have to show the relationship between the meter and the nanometer. So ask yourself, is there a direct relationship? And there is, because nano is a prefix, so we can simply indicate the relationship between the meter and the nanometer. And that relationship is 1 times 10 to the minus 9. So for every 10 to the minus 9 meters, that represents 1 nanometer. That causes your meters to cancel. That will simply leave you with nanometers. So if you take your answer and divide it by 1 times 10 to the negative 9, you're going to end up with a negative 397 nanometers. Now the way that you would report this, because we can't have a negative length. So this negative sign is simply telling you the direction that we're going. So think about absorption versus emission. Absorption means we're moving up. So that means that we're moving at a wavelength, an increase of 397 nanometers if we were going from 2 to 7. However, we're going from 7 to 2, so that means that emission is taking place. Remember, emission or emitting, but the process of emission indicates that you're moving to a lower level. So that negative sign, we won't actually show that in our answer. That's just telling us that we are emitting this electron, so we're moving to a lower energy level. And the length between these two is a decrease by 397 nanometers. So you would report this answer as 397 nanometers. So that's how you complete this problem. The key is making sure that you're understanding where you're starting at and where you're ending up at so that you can identify N1 and N2. And then remembering that this equation is actually 1 over the wavelength. So after you find that value, you have to do the inverse, so 1 over that, in order to get the actual wavelength. And then if you're needing to convert it to or report it in nanometers, you have to do an extra conversion. So I hope this helps. If you have any questions, let me know. Thank you.